Swayam Prabha. Digital India. Educated India.
Come back to real-time digital signal processing course. So, we have discussed about DFT in the last class. Today, we will try to cover FFT. So, to have a recap, we discussed about discrete Fourier transform in the last class and then how to use that for circular convolution. To give a flavor of it, so we will see the resolution what we discussed, how the interval or resolution in the frequency domain is going to get affected, whether it gets affected by padding zeros or not, what we will look at it. So, what we have here is how to check the frequency domain resolution. So, we call f as the resolution, which is approximated as 1 divided by n times t. We call this as hertz. T is a sampling period and then n is the number of DFT points what we will be taking it. So, which we can give it as delta f as the resolution named with f resolution, then we will be having n into delta f resolution. So, this is the time period between two samples. So, which is nothing but 1 by t, which is nothing but FSR hertz. So, what does it say? Frequency resolution is determined only by the length of the observation interval, that is what we call it as n here, whereas the frequency interval is determined by the length of the sampling interval. So, increasing the sampling rate, it means that expand the frequency interval and increase observation time, which will help our improving the frequency resolution. So, zero padding does not alter the frequency resolution. So, because resolution is going to be determined by the length of the observation interval, that is whatever n what we have chosen, and zero padding does not increase this length. So, to show this, so one can run MATLAB equation to see that how it is going to affect the resolution. So, we will take two complex signals with close frequencies, that one is with 10 hertz and one F2 with 12 hertz, sampled with the sampling interval t is equal to 0.02. So, it is going to be approximately 50 hertz. So, consider various data length, n is equal to 10, 15, 30 and then 100, and we will pad these n with rest of the values as 0. So, that it becomes 512 points and then run it in MATLAB. As you can see, for n is equal to 10, so which is what is the frequency we are going to have? F2 minus F1 is what we have is 2 hertz. So, what is our resolution? It is 1 by NT, which is equivalent to 5 hertz. So, hence these two signals are not bifurcated, as you can see only one is shown. So, as this thing what it is showing 10 times this basically as a 10 hertz thing. So, you are seeing it as 100 here in this. So, coming to the next one, when we substitute n is equal to 15 in your algorithm and then run, still this is not resolved. Why? Because our 1 by nt is equal to 3.3 hertz. So, that is the 2 hertz is less than the interval between the two samples. So, still you represent your 10 and then 12 as approximately 10 hertz itself. And coming with n is equal to 30. So, partly as we can see it is resolved. So, we are going to see two peaks in our DFT domain with n 30 samples, and then rest of them are 0 padded to make it 512 points. So, it is what is it? Our resolution 1 by NT, which is equal to 1.7 hertz. So, you will be, which is 2 hertz is greater than this. So, hence you will be seeing two waveforms peaks here which is appearing. So, when we go to n is equal to 100, so you will be clearly seeing them two peaks. Okay. So, it is dropping down to 0 and then again raising. So, this will be at 10 hertz and this will be at 12 hertz. So, what is the resolution here? We have it 1 by NT is 0.5 hertz. So, as you can see that whatever we claimed in the previous slide, that is 0 padding is not going to alter the frequency resolution. That is what shown in the next slide. So, coming with the next, why we have to go for FFT. So, initially we will take up radix 2 FFT. So, we will see that how we are going to derive our fast Fourier transform algorithm for our DFT. As we discussed in the last class, the computation of DFT is order of n squared actually, that is complex multiplication and addition. So, we will be seeing that how we can reduce it using butterfly structure. So, we are representing two butterfly ways of representing it. One is in the decimation in time, what we will be looking at it. So, your twiddle factors W n k is going to be fed here, and whereas in the decimation in frequency, it is at the output what you will be feeding it in. So, both have the same concept, and then what is the output here? So, we know that A will have real component plus the imaginary component what we are feeding A is equal to, and then B value also will be providing a real and imaginary, that is inputs are complex in nature. So, what will be the output? We will see in a while, which we call it as A dash here. So, we will be seeing that our twiddle factors W n k is nothing but e power minus j 2 pi k by n. So, which is expanded in cos and sine, you will be seeing it cos 2 pi k by n minus j sin 2 pi k by n. Okay. So, output A dash what we call it, when we expand this A with real and then imaginary, and B also with real and imaginary, and W n k with cos and sine function. So, this is what we will be getting it, that is A real plus B real into cos x plus B I imaginary part into sin x plus j times this is the imaginary part, this is the real part and this is the imaginary part of it. So, you will be seeing that. Same way even the B dash is going to be represented with real and then imaginary part separately. So, from this you will be seeing that how many multiplications, that is what we have real multiplication and addition, what you can count from it. So, I will be having 1, 2, 3 and then 4 multiplications, and then you will be seeing that 1, 2, 3 and then for the real part 2 additions and imaginary part 2 additions, taking into account my subtraction also. So, this is how what you can separate, and then B dash also we will be having the same amount. So, what we say is one complex multiplication leads to 4 real multiplications and 2 additions, what we are going to have it. Fine. So, if we apply the symmetry property, so then we will see how we are going to make our twiddle factors look like. So, W n into n k is given as we know that it is e power minus j 2 pi n n k divided by n. So, nothing but cos and sine what we have taken the thing. So, how we represent W 80. So, to show that our butterfly structure we will be taking n is equal to 8. So, this will be e power minus j 2 pi by 8 into 0, which is nothing but cos 0 minus j sin 0. So, we know that sin 0 is 0. So, cos 0 is plus 1. So, we will be getting 1 and then W 0 1. So, what it is going to be cos pi by 4 minus j sin pi by 4 and then W 8 2 will be represented as this and then it is nothing but cos pi by 2 minus j sin pi by 2. So, and then W 8 3 what we have is e power minus j 2 pi by 8 into 3 which is nothing but cos 3 pi by 4 minus j sin 3 pi by 4. So, how many coefficients we have calculated? N by 2 in this case for n is equal to 8. So, the rest of the thing that is 0 to 3 you can compute, rest of them what you can do is you can calculate it as W 8 4 is nothing but W 8 0 plus 4. So, which is nothing but minus W 8 0 which will be minus 1. So, you will be using the symmetry property here to get the rest of the coefficients. Same way W 8 5 and W 8 6 are calculated and then our W 8 7 remains same. Okay. So, to see that how the coefficients are calculated both cos and sin coefficients for n is equal to 8 has been plotted in this case. So, we know that sin starts from 0 and then how pi by 4 here and then pi by 2 and then next is pi by 2 pi by 3 and then how we will be going with values. And then cos we know that it starts from 1 basically and then how rest of the thing pi by 4 and then pi by 2 what it you are seeing it in this case. So, these are the 8 coefficients what we will be having it for our 8 point DFT that is discrete Fourier transform which we will be deriving it for our first Fourier time first Fourier transform basically. So, we will see first decimation in time. So, we said there are two ways of doing it, one is decimation in time, the other one is decimation in frequency. So, first we will take the time part of it. So, how we are going to bifurcate that? So, x of k is equal to we can combine take even parts and then the odd parts separately. So, that is what we name. So, two summations what we will be splitting it into. So, which is equivalent to our r is equal to 0 to n by 2 minus 1 x of 2 r, here n is replaced with r basically, for even it is going to be 2 r, for odd part of it, it is going to be 2 r plus 1. So, this is n by 2 minus 1 and here also it is going to be n by 2 minus 1 and we have substituted r is equal to 2 r. So, this will be W n 2 r k and here what we will be having W n 2 r plus 1 into k. So, now we will see that by combining it, that is 2 we are taking it out inside in this equation and r k goes here, we have separated it out into W n 2 to the power of r k, the other one term is W n k basically. So, which is not dependent on r. So, we can take it as a constant then take it outside in this equation. So, now we will see what is going to happen with our W n 2, which is nothing but e power minus 2 j 2 pi by n, which is when you split the thing it is going to be e power minus j 2 pi n by 2. So, we will name this twiddle factor as W n by 2. Fine. So, when we substitute that, so we will be ending up with x of 2 r W n by 2 r k and W n k the other one is x of 2 r plus 1 W n by 2 r k. So, we name this as g of k and this is h of k multiplied with W n of k, what is shown in here. So, now what is it? K is still going between 0 to n minus 1. So, whether we can also split this, that is what we are looking at, then what happens? X of k is g of k plus w k h k, and then if we go k to n by 2, then it is going to be x of n by 2 plus k to g of k plus w k h of k. So, these are the two terms what we will get it when we split k to 0 to n by 2, and the other part is n by 2 plus k to the values what we will be representing it. So, now continuing with the thing DIT part of it. So, we are naming g of k as this, we will give it as g r and w n by 2 to r k, and then g of we are going to split this into two parts again, even and then odd part g of k. So, then we give a new notation, that is L actually. So, this will be 0 to n by 4 minus 1. Earlier it was n by 2. So, we are bifurcating, dividing by 2. So, it is going to be n by 4 minus 1, and then this is going to be g of 2L into w n by 2 into 2L k. This will be 2L plus 1 w n by 2 into 2L plus 1 k. So, same way if we represent the thing g of k now, so we can have it as earlier splitting. So, we will be putting it as w n by 4 L k. You have to recall that we named it as w n by 2 r k earlier, now it will be L k. Bottom multiplied by 2, it is going to be n by 4, and then this is w n by 2 in to the power of k, and again 2 L plus 1 into w n by 4 into L k. So, same way we can split our h of k. So, because we had both g k and then h k here. So, the first we have bifurcated g k into two parts, h k we have to bifurcate. So, when we do that, it will be ending up in h of 2 L even and then odd part of it, n by 4 into L k, and then this becomes, as you can see, this was w n k. Then when we split the thing, so it will be becoming n by 2 here into k. This is the constant what we will have it, twiddle factor, and this is our normal one. So, then what happens? So, how we are going to define are all these coefficients. W n by 2 k is nothing but e power minus j 2 pi k n by 2, which is nothing but w n 2 k, and same way w n by 2 0 is nothing but w n 0. W n by 2 1 is now is equivalent to w n squared, and w n by 2 squared will be equal to w n by 4, which is nothing but w minus w n 0, and w n by 2 whole cube is nothing but w n to the power of 6, which is nothing but minus w n squared. So, you are seeing that this g of k is this n by 4 point DFT, and then h of k, the odd part of it is shown here, and further we will be getting our G0, G1, G2, G3. So, you are seeing this is input is x of 0, and then here x of 4, and then x of 2, and then x of 6 for the even part where you are bifurcating GK into even and then odd in this case. So, coming for n is equal to 8, now we will split the thing. So, what we have is this is my n by 4 point DFT, what you have it on the left hand side, and then we will be combining our weights in this case, and then this is the final output. So, how we will be feeding it? So, we had for the 2 of it. So, the other HK is split into 2 stages, as you can see, x of n and x of 5, and then the other one is x of 3 and x of 7. So, we will be having combining the thing, this is our output x 0 to x 7. So, now what we will do is we have all our inputs here. So, this we will see n by 4 point is nothing but only single butterfly in this case. So, we will replace this with a single butterfly and then put the weights here. So, we know that Wn 0 is equal to 1. So, we can avoid the multiplication here, and then we have minus 1 basically, that is how did we get the minus 1 here. So, you have to go back and then look into the thing. So, that is W 84 which is equal to minus W 80 which is nothing but minus 1. So, you will be seeing all of them will have the butterfly at the bottom minus 1 here. What we have is W n k here, W n this is n by 2 what we have the thing. So, when we this needs n log 2 n complex multiplications and complex additions. When I have the twiddle factors, it is in this way, that is we are representing y m minus first stage in this manner. So, now after splitting the thing, that is W n r n by 2 is nothing but W n to the power of n by 2 into W n r. So, which is nothing but minus W n r. So, I can provide the what is it. So, this is equivalent to minus 1 now. So, this is minus 1 here, and I can shift my W n k to here in the input of one of the input. Then what happens? So, our computation is going to reduce to half. So, then we will be needing n by 2 log 2 n complex multiplications and n log 2 n complex additions. So, this shows for n is equal to 8 the complete butterfly structures. In the second stage, you will be seeing that we need 2 coefficients, because the other one I have taken it as 1 equal to 1, and here also what you will be needing its 2 coefficients. Whereas, in the last stage what we have is 4 coefficients what is represented, but W 80 is going to be 1. So, we need 3 coefficients in this case. That way some of the multiplication, complex multiplications you can avoid. So, we will see that the computation complexity in a while. So, now we have compared when we discussed about DFT versus FFT. Now, after doing the FFT splitting of it, so we will be seeing that how we have reduced it. So, we know that we need in DFT n squared complex multiplications, and whereas in FFT with the shifting our twiddle factor to the input stage. So, we have achieved n by 2 log 2 n complex multiplications. So, with respect to that, we know that when n is of the order of power of 2. So, what will be the computations number of multiplications required by DFT and number of multiplications required by FFT, and only with respect to this we will be comparing our efficiency. So, it goes from 64:1 to 683 as the power of the computation we have to do increases by base compared to base 2, okay, 2 to the power of n. So, as it is increasing, so our efficiency is also going to increase. So, now one of the thing what we have seen is when we are doing this bifurcation, what has happened to our, here it is going to show us clearly. So, what I have is first is x of 0, next one what I want is x of 4, next I want x of 2 and then x of 6. So, we have done the bit reversal in this case. So, as you will be seeing in the equation here, so what we want is decimal number 0 to 7 what we have it when n is equal to 8. Binary equivalent is, as you will be seeing, 0 0 to 1 1 1, but input in the order what we want is 0, next is 4 what we want it, which is equal to 1 0 0, and then 1 0 1 0, and the next is 1 1 0 which is equivalent to 6, so on in the outside part. So, as we said that in DSP hardware we use the data address generator to do that. I think if you have to recall your architecture, I had given how to do this addition in hardware. As we know, n is equal to, in this case, 8. So, n by 2 is equal to 4. So, we know that the first one we are starting with 0 0, then we add 1 0 0. So, that is from left to right what we will be adding it. So, which gives me first digit is 0, next one is 4. Now, I add 1 0 0. So, I said we will be adding it in this way, 1 plus 1 is 0, we will be carrying 1 to here, 0 1 0, which will give me 2. So, you can go on doing that till the end. So, this is the data address generator which will be incorporating our bit reversal as the input or FFT computation. So, now we will see the how complex it is, how many groups we have, and then how many butterflies per group what we needed. So, that is, we said input signal must be properly reordered using a bit reversal, that is what we want it in the input. So, you can say that this is a 2-point DFT, which we can represent it as just a butterfly when it is a 2-stage point DFT. So, the next one is combine these 2 points DFTs from each stage. We will be having the next stage and then combine these 2-point DFTs, and then finally we will be combining 4 points here from each stage to get my 8-bit output. So, when we represent n is equal to 8, as you can see the thing, this is the first stage, this is the second stage what we have it, this is the third stage. So, now we call this thing as if we want to have, we can do in place computation. What do I mean by in place computation? That means these are the inputs, I can overwrite with these values with respect to this, because I do not need these values in the later stages. That is why we call it as in place computation. So, that I need not have to store my input more than 8 bits. And then next is how many stages we have to do. We say n is equal to 8, we have seen that we need 3 stages, that is log to n. So, which is going to be 3, and stage 1. So, we know that all the twiddle factors are 1, all are W80. So, which is 1 in this case, and last stage that twiddle factors are in sequential order. As we can see that here it is W80 and W82 what we needed. Here what we need is W80, 1, 2 and then 3. That is what the twiddle factors in the last stage is going to be in order. Now, we will see that some of the parameters with respect to our butterfly structures. Number of groups, how many I am going to have it. So, here you can see that we call each one as group. So, each butterfly basically. So, in the first stage we have n by 2, as we have taken n is equal to 8, 8 by 2 will be 4. So, you will be seeing 1, 2, 3, 4 groups are there in this case. Now, in the next stage I am going to have n by 4, which is nothing but 2 in this case, n is equal to 8. You will be seeing this is one group, this is the other group, and in the last stage we will have one group. So, 8 by 8 is 1. So, this is you are having only one group in the stage 3 in this case. Now, we will see how many butterflies per group are going to be there. In the first stage we have one butterfly. So, in all the groups we have only one butterfly. Coming to stage 2, so as you can see these are the 2 groups. I have 2 butterflies in this group, and here also we have 2 butterflies. When I come to the next stage, stage 3, then we are going to have n how many butterflies? 4 butterflies in the group here. So, you will be seeing that this is one butterfly, second, third and then fourth butterfly. So, that is what it is going to be, and number of stages are more, then what we will say in the stage log to n, we will have n by 2 butterflies. So, something should be striking. If it is n is equal to 16, then it is going to be 8 butterflies in the last stage. Okay. And then what is it? We call it as dual node spacing. So, between the two nodes, what is the spacing? I am going to have it here 1, because x 0 and x 4, these are the two nodes, the spacing is only 1 between them. When I come to stage 2, we will be seeing that the spacing is going to be 2 nodes. So, I am taking one from here, next one is coming from this. So, there will be 2 node difference, what I will be giving it as input to this. Same way you can calculate everywhere, and in the stage 3 I will be having this thing, dual node spacing is going to be 4. I think it should be something striking, equivalent to your butterflies per group, and then node spacing is also same. Okay. These two columns almost repeated. So, you will be seeing that this is the first input, the next input from the fourth one. So, if I take in this one 2, 3, 0, 1, 2, 3 and then the fourth one. From here what I will be taking it. So, there will be spacing of 4 nodes for this. Now comes the twiddle factor exponents, how we are going to put it in each node. So, we will be having n by 2 into k. In this case, in the stage 1, k will be equal to 0. So, that means to say I will be having 8 WNKs which are all 1. Okay. So, that is the reason why we do not have any, we can remove this W80 equal to 1. So, 8 of them are there. So, we which is equivalent to 1 in this case. So, the next one in WNK, what we have put it, k is equal to 0, that is why it becomes W80 and it which is equivalent to 1. So, in the second stage what we are going to have is n by 4 into k, k will be going between 0 and 1. So, you will be seeing that this is W80 and then k will be 1, then it is going to be W8 into 2 in this case. So, the last stage what it will have, our stage 3 in this case is going to be our last stage, n by 2 into k, 0, 1 and then 2 are the values. So, W80, W81, W82 and W83. So, we will be having 4 of them here, and when we have more than that, what will be the thing? K will be going between 0 to n by 2 minus 1. So, you will be seeing here n by 2 is 4, 4 minus 1 is 3. So, that is why we have k is equal to 0, 1, 2 when n is equal to 8. So, coming with this thing, as we said, we can have the computation either in the time domain or in the frequency domain. So, that is we call it as decimation in frequency, FFT. So, we say that output signal must be properly reordered using a bit reversal algorithm. That means to say input is in order and output will be in the bit reversal order in the DIF case. So, here also it is in place computation compared with your DIT, decimation in time, and here also number of stages is going to be log to n. And what we say stage 1, all the twiddle factors are in sequential order, and last stage all the twiddle factors are going to be 1 in this case. So, you will be seeing that in decimation in frequency is equivalent to reverse of your decimation in time. So, how the number of stages and other things it looks like, you will be seeing it. Number of groups in this case is going to be 1 for n is equal to 8 what it is shown, and then number of number of groups in stage 2 is going to be 2, and then last stage in this case is 4. So, it is equivalent to log to n stages the stage thing will have n by 2 number of groups, and then you will be seeing the butterflies per group will be n by 2, n by 4 and n by 2, and last one will have 1 basically per group. And then your dual node is equivalent to the previous case, basically this is the one. Now only the thing is twiddle factor exponents. So you will be seeing that n in this case, there it was a k was the variable, here it is going to be n. N will be going between 0 to n by 2 minus 1 will be your twiddle factor first stage, and in the second stage it is 0 to n by 4 minus 1, and so on what you will have it. In the last stage you will be having n is equal to 0 and n by 2 twiddle factors, which becomes equivalent to 1 in this case also, as you can see it. Okay. So, now we will look at the finite word length effects in FFT. Thank you. So, we have seen how to get our FFT using butterfly. So, in the next class we will look at the finite word length effects in FFT, how it will be affecting our outputs and what is the care we have to take it. Thank you.